So my name is Michael King. I'm currently a Ph.D. candidate at Memorial University of Newfoundland, working under the supervision of Dr. Kim Welford. And today I'm going to be sharing some of my recent PhD research, which is focused on looking at continental blocks along North Atlantic rift margins and looking at how we can use deformable plate reconstructions to understand their kinematic and crustal evolution. So with this session on microplates today, we're kind of acknowledging and appreciating the fact that tectonic plates come in all shapes and sizes. And many of us have probably seen this map of Earth's main tectonic plates at some point in our careers. But oftentimes when we look at tectonic regimes, or in particular for today, rifted margins in a bit more fine detail, we can see that this map can become a little bit more complicated. In particular, today I'm going to be showing you how we can potentially see this in the North Atlantic. So roughly kind of this area kind of spanning this black box shown right here. So if you start off by just looking at a simple screen grab from Google Earth, and I'm going to draw your attention kind of where I have labeled the North American plate here. So if we start onshore and go offshore onto the continental shelf on the Newfoundland margin, we can see that the continental shelf is quite variable in terms of its geometry. And in some places, we can kind of see what look to be these kind of little continental blocks here that appear to be almost ripped apart from the continental shelf itself. And these are basically the continental blocks that I'm going to be talking about in particular for my talk today. So the one that I just pointed out is referred to as the Flemish cap here along the Newfoundland margin. And we also see other examples of these on other margins throughout the North Atlantic as well, such as the Porcupine Bank here along the Irish margin, and also the Galicia Bank along the West Iberian margin. So thinking about rifted margins in general, and in particular magma pore rifted margins, so you can think about the figure on the right-hand side here as a general way we see these form. So oftentimes we start off with a period of crustal stretching, which leads to thinning of the crust, and then we thin the crust enough that often leads to things such as hyperextension or exhumation of the mantle. And you can think of panel D here as almost a potential final rift template. So there's all kinds of interesting domains and features here. And kind of the areas that I'm going to be looking at today with my talk are these continental blocks or these potential microcontinents. And in terms of understanding kind of the processes and mechanisms of how these form, this has been studied in previous studies. One recent one is from Newhart et al. 2021. So they looked at microplate formation by interacting propagating rifts. So if we look at the figure on the top left here, so basically we have one rift here, another one here that are spaced about 300 kilometers apart. And basically as they propagate towards one another, you basically get the localization of a microplate here. And today I'm going to be looking at this in terms of examples of where we see these in the North Atlantic, and also looking at the kinematic and crustal evolution using deformable plate reconstructions. So understanding where we see these throughout the North Atlantic. So one way to get kind of regional perspective on where we see these continental blocks is using crustal thickness estimates that are computed using 3D gravity inversion. So that's basically what we're seeing here on the left-hand side of this map. So if we look at the color bar, basically the blues represent areas of relatively thinner crust, and the greens represent areas of relatively thicker crust. So for example, if you look at the Newfoundland margin over here, we can see that the crustal thicknesses are quite variable present day, and we see these continental blocks stand out pretty good. So for example, the Flemish cap is kind of shown right here. So this continental block ranging in thickness from about 25 to 30 kilometers thick. As I mentioned on my previous slides, we can also see these examples in other places too, such as the Porcupine Bank over here on the Irish margin. But of course, gravity inversion is very non-unique, so we really need also other data sets to try and constrain where we're seeing these crustal thickness variations and where we're interpreting these blocks. And one way we can do this is by using other data sets such as seismic refraction profiles, for example. So here we have this profile A prime, that's modified after Prompovitic and Manischal 2010. So for example, we can see the various features too in the Orphan Basin, such as the failed rift in the West Orphan Basin, various crustal highs within the Central Orphan High, and of course, kind of the main areas of interest for my talk here today, these continental blocks, such as the Flemish cap. So in terms of my PhD research, so one of the main objectives is just looking at the kinematic and crustal evolution of these blocks using deformable plate reconstructions. And in particular, if we look at kind of the general geometry of these blocks on the map on the left-hand side here, given by the yellow polygons, we can also see that they're bordered by sedimentary basins that have undergone various amounts of crustal thinning. So basically trying to also understand what is the role that they potentially play during deformation of the rift basins. And something interesting that we also aim to look at through my PhD, I'm going to advance my slides here, not working, not sure why. There we go, sorry about that. So the continental crust that makes up these margins is also quite variable in terms of their ancient orogenic terrains. So for example, if we look at the map on the left-hand side here, and we look along strike of both the Newfoundland and Irish margins, we can see that these ancient Paleozoic terrains and boundaries can vary quite a bit along the margin. So potentially seeing what role do these terrains and boundaries had to play in terms of the subsequent rifting in the Atlantic, and do they have any kind of potential Or is there any potential interplay also with the kinematics of these continental blocks? So to do this, we're going to be using deformable plate tectonic reconstructions. So these are built using the G-Plate software, which is a software that's open access and free and built by the Earthbite group at the University of Sydney, Australia. And it also has a Python programming library that we can use to our advantage as well, called PyG-Plates. So the basic premise of deformable plate reconstructions is, basically similar to rigid reconstructions in the fact that we're basically, reconstructing tectonic plates and microplates back through time. But one of the advantages of deformable plate reconstructions is that basically we can quantify crustal stretching and temporal variations in crustal thickness within these predefined regions within our plate kinematic models. And to kind of describe the basic way of how we build these, just going to refer your attention to the figure on the right-hand side here. So with all models, we need to start with model inputs. So with these deformable plate models, we need to define where the deformation is going to take place. So first, we would often need to define an exterior boundary, such as this blue boundary right here. So that could represent something such as continental ocean boundary or the edge of continental crust. An interior boundary, such as red boundary right here. And then basically within these boundaries of deformation, we can have whatever features we want, such as the microplates or continental blocks that we're interested, shown by kind of here the green polygon, or we can also define them as points. So then basically once we have these model inputs, we can use them to construct what's referred to in G-Plates as a topological network. So basically what this does is that it creates a triangulation mesh that allows us to measure strain rate. And basically this varies based on the plate kinematic inputs that we put into our model. And this is advantageous because once we're able to measure strain rate, then we can also input a present-day crustal thickness model into our reconstruction. So these can be, for example, the gravity inversion crustal thickness estimates that I showed at the beginning of my talk. And then we can actually reconstruct these crustal thickness estimates back through time. So kind of the main workflow is that we're reconstructing these crustal thicknesses back through geological time. In terms of rift and margins, this can be advantageous because we can reconstruct things such as pre-rift templates and also assess the deformation that's experienced within the blocks and basins through time as well. And just to kind of try and drive home the point in terms of the difference between rigid and deformable reconstructions, as is what I got at in my previous on the previous slide. So on the left-hand side here, we have a rigid plate reconstruction of the North Atlantic back to 200 million years ago. So we see we have all kinds of different plates and blocks and boundaries that are overlapping each other. And basically the advantage of deformable reconstructions is that we can avoid some of this overlap and basically add kind of these predefined areas where we can evaluate strain rate and deformation throughout the model history. And we can also, as I mentioned, put in a crustal thickness model here and understand how that gets reconstructed back through time. And just to really drive home the point in terms of what I'll be doing here today. So again, just to kind of give a bit more applied example. So here we have a deformable plate reconstruction along the Newfoundland margin defined by kind of where I'm pointing my laser pointer here. And we also have crustal thicknesses on Newfoundland margin on the inside. But one thing I also want to emphasize is that we can also reconstruct other data sets if you wish. So for example, magnetics data throughout the Newfoundland margin here. So again, we have the same deformable network here, but except we have magnetics data. So then when we reconstruct this back through time, we can see that, for example, if we reconstruct it back to 200 million years ago in panel A1 down here, we can see that the potential pre-Jurassic crustal thickness template of the Newfoundland margin here. We can also compare where we're seeing these crustal thickness trends to what we're also seeing in the reconstructed magnetics data. So trying to make comparisons between the two and see how that can guide our interpretations. So now that I kind of get a walkthrough of the workflow, I want to give a bit more of an applied example of how we use this methodology to look at the North Atlantic, and in particular continental blocks. So this is an example from our recent paper, King and Will for 2022B. So describing the model inputs can be mostly described by this map on the right-hand side here. So the crustal thickness estimates that we'll be reconstructing back through time are along the Newfoundland margin, Labrador margin, Irish margin, and West Iberia margin, shown right here. And in terms of the continental blocks of interest, so again, just to kind of take a step back, so the region of deformation is defined by this black boundary here, the edge of continental crust, and also this red interior boundary right here. And then we're also reconstructing some main continental blocks of interest. So for example, Flemish Cap shown right here. And I'll note that we're also designing this as points because basically the advantage of designing these blocks as points allows for the triangulation mesh to be kind of expanded within the interior of the block, and also allows it to kind of be relatively deformed through geological time, as we kind of expect. And we also include the Southern Grand Bank's tail down here, and along the Irish margin, we also have the Rockall-Hatton Bank and the Porcupine Bank over here as well. And in terms of the poles of rotations and model boundaries, these are modified after PCL 2019, and basically we're going to be evaluating this model from 200 million years ago, so the pre-Jurassic to present day. So basically, if we take this model and we can reconstruct it back to 200 million years ago, this is essentially what we get here on the right-hand side. So again, this is kind of the 200 million year crustal thickness template of the model I just showed. And kind of just before I play the video that's here, I just wanted to touch on some key observations that we see in terms of the pre-Jurassic template. So we can definitely see here that it's quite variable. It's definitely not something that's constant and uniform. We see quite a bit of variability in the pre-Jurassic template here. So for example, on the Newfoundland margin, we can see quite a bit of variability in the crustal thicknesses that we're seeing. And we can also see the pre-Jurassic nature of the continental blocks, kind of these thicker areas of crust that we're seeing here, such as the Flemish cap along the Newfoundland margin. And then as I start to play this video, we'll start to see how kind of the deformation and crustal thicknesses are partitioned and segmented through time, especially within the blocks and basins. So I'll have to... Good, I'll play the video. So again, the time frame is kind of shown up here. So basically, we start seeing some of the rotation of these blocks. So for example, we see the rotation of the Porcupine Bank causing crustal thinning within the base, the Porcupine Basin here. Similar within the Orphan Basin, we start seeing the Flemish cap rotate, especially when Iberia starts to take off. We see the deformation within the Galicia Interior Basin here. And then as we get kind of closer to present day, we start seeing that deformation migrate to the northwest into the Labrador Sea and Baffin Bay. And one of the things that I wanted to focus on where this talk is on continental blocks and microplates in particular is the pre-Jurassic template of the North Atlantic in terms of the crustal thickness estimates that we're seeing. So one of the things that I wanted to focus on in particular, like I said, is the pre-Jurassic nature of the continental blocks. So basically, after evaluating the results, we can kind of divide these blocks in what I'm referring to as primary versus secondary blocks. And these primary blocks are model inputs, and they're very large in size. So some examples that I've already talked about are the Flemish cap, kind of shown right here, for example. And these primary blocks really do have a big impact on the deformation that is experienced within the basins, but they also have an impact on basically the evolution of what I'm calling these secondary blocks. So these secondary blocks are basically blocks that are not model inputs, but they actually kind of form organically, if you will, throughout the model. So for example, we see the Galicia Bank kind of shown right here on the West Iberian margin, and also the Orphan Knoll kind of indicated by this green star right here within the central part of the Orphan Basin. So it really seems like these primary blocks having a big impact both on the deformation within the basins, but also the evolution of these secondary blocks that I'm referring to.
Okay, Michael, that's like 12 minutes.
Okay, thank you very much. We're almost done here. And then one of the other things I also want to talk about was the crustal segmentation that we're seeing and the kind of the variability in the crustal thickness template. So if we look at the right-hand side here in panel B, we can see that a lot of the crustal thickness trends and kind of segmentation that we're seeing also align with potentially where we're seeing these onshore to offshore Paleozoic terrain boundaries. And that's something that we've actually been looking at quite a bit lately. So we see a lot of it in the Orphan Basin, also on the Porcupine Bank and to the south, kind of along the southern Grand Banks. But of course, kind of saying that, potentially these orogenic terrain boundaries have a really big impact with respect to the pre-Jurassic template of the North Atlantic. And that's something that we've been investigating a little bit lately in terms of trying to expand our reconstructions actually deeper in time. So I'm going to be presenting this work actually at EGU. So if you're interested in this kind of thing, feel free to come to my talk. So before I play the video, basically what we have here, so basically the yellow points represent the deformed orientation of the coastline relative to the black ones, which are the present day ones. And basically we're going to be reconstructing these crustal thicknesses forward in time. And basically Atlantic Canada was largely influenced by strike slip deformation. So we can kind of see it has a big impact on the formation of the Carboniferous basins and also potentially what happens in the Orphan Basin prior to rifting of the Atlantic and following the Beriscan orogeny as well. So that's kind of just a teaser trailer while I'll be talking about EGU. But in terms of the conclusions and kind of future directions based on what I gave today a bit in my talk, these deformable plate reconstructions definitely served as a nice tool in terms of trying to reconstruct these continental blocks within the North Atlantic. And in terms of results, we can definitely see the kinematic role of these blocks and their potential correlation or interplay with orogenic inheritance. So we definitely see some strong correlations between where we see onshore to offshore inheritance and also where we see segmentation or crustal thickness results and how that's evaluated through time. And moving forward, it seems like the talks ahead of me will also talk a bit about this, but I think getting a better understanding of the processes and mechanisms that really drive these continental block kinematics, I think is going to be really important to get a better understanding of that and kind of try to validate what we're seeing in our plate models. And also, of course, improving the model inputs and also trying to be able or develop a better way of quantifying uncertainty within these models. So that's everything I have to say. So thank you very much for listening. I'm happy to take any questions. So thank you.
Thanks, Michael. Great. Any questions from the audience? Just raise your hand or speak up. Type in the chat. Okay, if not, I guess, Sasha, you had a question.
Yes, thanks, Derek. Thanks, Michael, for this great talk. I was wondering when you say that you use gravity inversion to get the crustal thickness that you reconstruct. How do you deal with material additions, sedimentation, magmatic additions, things that are added to the continental crust during rifting? How is that taken into account?
That's a great question, Sasha. So currently, basically the way that the gravity inversion is done, so those additions are often excluded because basically the gravity inversion approach that we use basically kind of excludes anything that's additions in terms because it's basically what it does is that it gives us a 3D density model. So basically to get the thickness of the crust, we basically extract an isochron representing basically the depth between the basement and the moho. So oftentimes those extra additions are excluded from our gradient inversion crustal thickness estimates. But I know there's other approaches that sometimes also take, I guess, extra steps to try and also account for those. So I guess long story short is that they're not really accounted for on this. And I find sometimes when you see areas that are a bit thinner, sometimes they correlate to areas where we do see those magmatic additions. So it's definitely something to kind of consider, I guess, in the future of these reconstructions and how we, I guess, apply this approach. But it's a good point.
Great, thank you.
Any other questions from the audience? Okay, I have a question actually, it's very similar. I have the same question as Sasha, but I've got an additional one that's kind of built in it. Am I right in thinking you're reconstructing the crustal thickness back in time, right?
Yeah. Yeah.
So also, so what kind of like stretching model do you assume? Like assuming there's no additions to the crust, then how do you decide what rifting model to reconstruct the thickness back with?
Yeah, so I guess it fundamentally comes down to, I guess, your plate reconstruction of interest. So I guess I show one model today, but I guess there's a lot of plate reconstructions of this region. So I guess first off, starting off simple in terms of just looking at the plate reconstructions of the larger plates, but then I guess it gets much more difficult when you go deeper back in time because you also don't have any more oceanic isochrons anymore. So you start accounting for these smaller plates in between. So really in terms of trying to, I guess, pick what stretching model you use, I guess you kind of would, in terms of what I've done so far, try to evaluate each one and see how it lines up with the independent observations, I guess. So things that we're seeing from seismic sections and things from the well data and stuff like that, and trying to constrain the timing of deformation from that. But it's definitely something to look at in the future in terms of trying to improve the ways that we can do that, and also, I guess, quantify the uncertainties of these models versus, another model, for example. So it's a good question.